Some of the most powerful ideas in computer science don't start out with lines and lines of complex code. Nope, they start with simple puzzles. And today, we're going to take one of the absolute classics to unlock a way of thinking that can help solve almost any complex problem. Let's dive right in.
All right, so here it is, the classic puzzle. You've got two jugs, no fancy measuring lines, and a water source. How in the world do you get exactly 4 gallons? Now, sure, you could just slosh water back and forth and hope for the best. But what if there was a guaranteed system, a way to actually map out every single possibility so you could find the solution, or maybe even prove that a solution doesn't exist? Well, that's the system we're going to build today.
So here's our game plan. First, we're going to turn this little puzzle into a formal, rock-solid problem. Then we'll get into this core idea of a state. It's how we'll track every possible situation. After that, we'll map out the entire problem space, and I'm going to let you in on a secret weapon, the invariant principle, that helps us navigate it. And finally, we'll see how all this applies to, well, to just about everything.
The first step to cracking any really tough problem isn't to start guessing. No, it's actually the opposite. It's to stop, take a step back, and create a perfect blueprint. We need to define the rules of the game with absolute mathematical precision.
This quote from our source text, Mathematics for Computer Science, just hits the nail on the head. This whole process is called problem formulation. It's all about creating a clear, logical game plan before you even make your first move. You're setting up the rules so there are absolutely no ambiguities. So how do computer scientists actually build this blueprint? They use something called the axiomatic method. Now, it sounds super fancy, but the idea is actually pretty simple. You start with the absolute most basic truths of your system, the axioms. For our puzzle, an axiom is something like, you can fill the 3-gallon jug completely. Another one is, you can empty the 5-gallon jug. By listing every single one of these basic unbreakable rules, we create this solid foundation to build our entire solution on. Okay, so we've got our rules. Now what? Well, we need a way to talk about where we are on the puzzle at any given moment. We need to be able to take a snapshot of the situation. And this brings us to a really crucial concept, the state. A state is really just a precise description of the system at one point in time, a freeze frame. For our water jugs, we can describe any state with just a pair of numbers, like 3, 5. That just means the 3-gallon jug is full and the 5-gallon jug is full. Or 0, 0 means they're both empty. And just think about what we did there. We took a messy, physical puzzle and turned it into simple, clean pairs of numbers. And here's how our rules connect to our states. When you apply one of our rules, you create what's called a state transition. You literally move from one snapshot to another. So in this token game example, one simple rule takes you from the state 3, 5 to 2, 8. For our jugs, the rule, pour the 3-gallon jug into the 5-gallon jug, transitions us from the state 3, 0 to 0, 3. Simple as that. Okay, let's just pause and think about what we've got now. We have locations, those are the states, and we have the roads between them, those are the transitions. What does that sound like to you? That's everything we need to draw a complete map of our problem's entire universe. Building this map, or what we call a state machine, is basically a 3-step recipe. First, you list out every single possible state, every combination of water in our jugs. Second, you define all the legal moves, or transitions, that can get you from one state to another. And boom, just like that, you have a complete map of every single thing that can possibly happen in this puzzle. And here's what that map looks like in a more formal sense. For that token game, this simple table defines the entire system. It tells you from any state you're in exactly where you can go next. This table, as simple as it looks, is the complete guide to the problem. And this right here, this is the crucial point. We've managed to transform a messy, confusing puzzle into a simple navigation problem. This state space is our map of all the reachable locations. The solution? It's just a path on this map from our start state to any state where one of the jugs has exactly 4 gallons. The problem is no longer about guessing. It's about pathfinding. But wait a minute. This map could be huge, right? I mean, absolutely massive for a complex problem. So how do we navigate it? Is there a shortcut? A secret weapon? Yes, there is. And it's one of the most beautiful and elegant ideas in all of computer science, the invariant principle. So what is an invariant? It's a property of the system that never, ever changes. No matter what legal move you make, this property holds true. It was true at the very beginning, and it'll be true in any state you can possibly reach. It's kind of like a law of physics for our little puzzle universe.
Let's make this totally concrete. Imagine you only have 10-cent and 15-cent stamps. What's an invariant here? Well, the value of every stamp you have is a multiple of 5, right? That means any total amount of postage you can possibly make must also be a multiple of 5. That property is the invariant, and it immediately proves that reaching a total of, say, 26 cents is impossible. You don't have to try. You just know. The invariant principle instantly shows us which parts of our map are completely off limits.
So, we've gone all the way from a simple water jug puzzle to states, state spaces, and these powerful invariants. But why does this matter? Because this way of thinking, this whole framework, it doesn't just solve little puzzles. It's used to tackle some of the biggest and most complex challenges in technology.
I mean, think about this. Every time you use a piece of software that doesn't crash, you're benefiting from this exact method. A computer program is just a massive state machine, and invariants are used to prove that bad states, like a program crashing, are completely unreachable. This logic is used everywhere, from designing reliable networks that run the internet to forming the very bedrock of modern artificial intelligence. What you've just learned is a fundamental tool for thinking systematically about any complex system.
So, I'll leave you with this thought. We started with a simple puzzle and ended with this incredibly powerful framework for reasoning. What if the most complex challenges we face in the world are really just incredibly vast state spaces that we just haven't taken the time to map out yet? What if finding the solution is just a matter of defining the states, mapping the rules, and discovering those hidden invariants? What could we solve then?